We will start with the topic on introduction to adjustable speed motor drive systems. So in this class, we will look at the different type of motors, the different types of controllers, the power electronics and harmonics, and also how to calculate the power if a particular waveform has different types of harmonics. So in the variable speed drive systems, the main components are electric motor. It can be DC motor or AC motor. In AC motor also, there are different types of AC motors. We will look at them. Then power converter depending on the type of motor. So we need to understand the power converters, which you have already gone through in your previous classes or previous courses. So they are rectifiers, choppers, inverters, and cycloconverters. So understanding of the power electronics and power converters are very important because the power electronics is the enabling technology for the control of motors and achieve the required torque and speed from the motor. Okay. So the rectifiers basically are the ones which convert AC to DC, choppers from DC to DC or DC-DC converters. Inverters are DC to AC inverters, and cycloconverters are AC to AC converters. Then we need controller. That is the matching the motor and power converter to meet the load requirements. Okay. The controllers will help to achieve the required torque and speed. For example, if you need 1000 RPM, so when you put a sudden load, then the speed can change, but the controllers will help to bring back the speed to 1000 RPM. Then we need to understand about the load because the load characteristics depend on the way the motor is selected and also the power electronic system. So the load torque determines the motor torque. Okay. And the load torque and speed together will determine the power that is required from the motor. P is equal to torque times omega. Okay. Torque in Newton meters, power in watts, and this one radians per second. So if you know the motor power, then you can determine the power ratings of the power electronic devices. And then also we can select the power of the source. So this is a basic configuration of an adjustable speed drive system. So we have a motor. This motor drives a load on one end. So this is the load. Okay. The input to the motor is coming from an inverter. This is an AC motor. That is why we need an inverter. If it is a DC motor, we need a chopper or a DC-DC converter, provided the source is also DC. So then, where do we get the power from? Power is coming from the grid or AC power supply. It can be 480 volts, 60 hertz, three-phase. So this is a fixed frequency, fixed voltage system. In order to control the speed, we need the variable frequency and variable voltage. Why variable voltage? Because the voltage has to be varied proportional to the frequency. The speed depends on the frequency and the number of poles, because number of poles are fixed. Generally, the frequency controls the speed, or the speed is directly proportional to the input frequency of the motor. Okay. Then this is the controller, the regulator, which regulates the speed and the torque. Okay. So the load is shown here, but it is driven by the shaft. So So from the load, we need to measure the signals, so that, for example, we may want to measure the speed, or from the inverter output, we want to measure the current, voltage, etc. So we need these sensors. So for example, if you have an electric vehicle drive system, it has a motor which drives the wheels, and this is an AC motor, and the inverter supplies the variable frequency, variable voltage to this motor to achieve the required speed and torque. So battery is the source of electric power in an electric vehicle, and this converter is the one which converts the battery voltage to the required voltage at the input to the inverter. But sometimes we may not need this converter. We can directly connect the battery output to the inverter, and the battery has to be charged from a charger. Okay, and also there is a DC-DC converter to charge the 14 volts battery in the vehicle. So here the motor plays a main role in the electrical propulsion system. So at the end of the semester, we can also review about more about the electric vehicles, and we will have a class on how to select the motor, the power electronics, and all those things for a particular electric vehicle. So why are we using adjustable speed drives? Why they have to be adjustable speed drives? A certain process has to be done at a certain speed. For example, if you have a paper machine, in order to produce the paper, it has to move at a certain speed. Or if you have to produce the cement, the kilns have to be rotated at a certain speed. So those loads like kiln or a paper machine drive systems, they all have to be rotating at a certain speed. So in order to achieve that one, we have to drive them from the electrical motor. And also it has to provide the torque. The motor has to provide the torque that is required to drive the load. So in order to provide the torque, we need to drive at a certain speed, okay, to achieve the required torque at the given speed. And also if you have the variable speed drive system, then you can have energy savings, because then the optimum operation can be achieved. Means certain loads are optimum from the efficiency point of view if they are driven at a certain speed. So once you save the energy, then also you draw less electricity from the grid, and it reduces the cost. And also it will improve the stability of the system. You can drive the operation smoothly, and also you can have the soft starting of the system. Okay, and many of the standard induction motors can be used, and also we can also control the power factor of the motors by having this power electronic system and the variable adjustable drive system or variable frequency drive system. So also it improves the life of the motors, because we can control the transient torques, the thermal heating, starting, and also the how much is the inertia loads, and also during the inertia, high inertia loads, the drawing of the high current from the source can be controlled. And we can have a forward reverse, forward motoring, forward generation, reverse motoring, and reverse generation operation. And also we can have regenerative braking. That is, we can have the energy from the motor feeding back to the source. For example, in electric vehicle, when you try to decelerate the vehicle, or when the vehicle is going down the hill, Then the motor acts as a generator, and the generated energy can be converted to required form, and it will charge the batteries. Okay. So some of the applications of the adjustable speed drive systems are fans. We can have variable speed fans, pumps, compressors, conveyors, mixers, processing lines in processing power plants, blowers, extruders, winders in, for example, rolling mills winders, or in paper mill. We all use the winders, cranes, lifts. Everywhere we need the electric motor. So when we have the electric motor, then we need to have a variable speed operation. So that is achieved by the power converter. And also we have a very high voltage drives. They are medium voltage drives of the order of 1 kV to 15 kV input. So a medium voltage drive also has as an input, then a transformer. You can use it to step it down to the required voltage or even step up. Then AC to DC. Then this is a DC. DC goes to the inverter. And this may not require at all places, this transformer, but in some applications, for example, if that output frequency is fixed, then in subsea applications, for example, and you have a long distance cable, then you can have the transformer. Otherwise, the inverter output directly goes to the AC motor. The voltage range for a medium voltage system is up to 15 kilovolts. Okay, and most of the applications are around 4160. For example, even in the marine applications, they use this voltage. Power can go up to 30 to 35 megawatts, but most of the power for medium voltage drive systems are around 1 to 4 or 5 megawatt systems. So other applications of medium voltage drives are petrochemical. For example, in pipeline pumps, gas compressors, mixtures, submersible pumps, boiler feed, water pumps. There are many applications where the motors are required. The 60% of the energy that is produced in the world is consumed by the motors. Then even for producing the cement, we have to have the motors driving the kiln. Then in addition, we need to have forced draft fans and preheat tower fans and many other equipment. They have to be driven by the motors. Okay, so then if you operate them at a variable speed operation, then we can achieve the optimum operation with maximum efficiency. So they are used in fan pumps, boiler feed water pumps in forest product, refineries, water or wastewater treatment applications, mining, commercial, paper mills, rolling mills. Okay, in steel mills, they are widely used because the basic format that is converted from the raw material is the blooms. They are like this, and then they go through the rolling mill to achieve the desired shape, whether it is a wire or a rod and all those things. They are all done by the rolling mills. Then there are winders also. Okay, in subsea applications, that is for the production of oil and gas from the ocean. Then they use it for submersible pumps, compressors, etc. And there are many other applications in addition to what I've already mentioned. So now let us see what type of electric machines are used. So the electric machines can be either DC machines or AC machines. So DC machines have a commutator segments. Okay, that is those copper bars. So they can be wound field or a permanent magnet field. So on an AC motor is a stator and a rotor, and a DC and fed by AC, and a DC motor as a DC. And there are different types of DC motors, which we have seen when we were studying about the DC drive systems. So I'm not going into detail. And the field can be a wound field, like in a series DC motor, shunt DC motor, or in a separately excited motor. It is separate from the armature. Or it can be a permanent magnet field. So this can be a permanent magnet, so you don't have to have an external power supply to vary the field, which in turn varies the flux. But the flux is fixed. So this wound field can be series, shunt, or separately excited, which we have already discussed. The AC motors can be either induction or synchronous. In induction, we have a wound field synchronous motor, or a wound field induction motor, and squirrel cage induction motor, which we have seen in the which we are going to see in the next class or after that. Okay, and DC motor drives is the next topic after the introduction. That is where we are going to discuss more on the DC motor drives here. And then the AC motors, one is the synchronous motors. What is a synchronous motor? Synchronous motor means it runs at the synchronous speed. So NS equals 120 F by P. Suppose if it is a 4-pole under 60 Hertz, what is the synchronous speed? NS equals 120 times 60 divided by 4, that is 1800 RPM. Right? So the rotor runs at 1800 RPM. In asynchronous motor, for example, in induction motor, it always runs below the synchronous speed. The rotor always, as a motor, it runs below the synchronous speed. So it can be 1710 RPM or 1750 RPM, depending on the load or the slip. Okay. So in the synchronous motors, we have a wound field motor, permanent magnet motor, and also reluctance motor. The permanent magnet motors can be permanent magnet brushless DC motors, or permanent magnet brushless AC motors, or permanent magnet sinusoidal back EMF motors. They are also called. These are the trapezoidal back EMF motors. And these are sinusoidal back EMF motors. Okay. So this is an induction motor, how it looks. This is windings motor. And this is the rotor. This is the stator here. The stator windings are there. Okay. The rotor doesn't have a windings. It is a squirrel cage. So there are short-circuited windings, or the rotor bars, which are short-circuited. And then the synchronous reluctance motor, permanent magnet motor, switch reluctance motor, PM axial gap, they are all AC motors, and they all run at synchronous speed. So permanent magnet motor, the stator of the permanent magnet motor is similar to induction motor stator, but the rotor has a permanent magnets. And switch reluctance machine is different. It has a laminations on the rotor, and stator also is different than the PM or synchronous reluctance machines. We'll see later. The PM axial gap machine looks like this. It looks a very different way than the other types of motors. So in electric and hybrid vehicles, for example, we use mainly these days interior permanent magnet motors we use. Then there are several types like surface mount motor. That is, the permanent magnet materials are mounted on the surface, interior are buried inside the rotor, concentrated winding, or the windings of the stator are wound in a different way. So like this, more or less. So this is the PM motor, and this is the switch reluctance. Okay, and this is the synchronous reluctance. So what are the considerations for selecting the motor? So we need to have the motor which has a good torque speed characteristics. It is very important to have a motor with a good torque speed characteristics. It should be rugged, and it should be able to operate at a higher peak value, at least for a few minutes or seconds, depending on the application with respect to the continuous power rating. If the continuous power rating is, say, 20 kilowatt, we should be able to operate, say, 50 kilowatt. If it is designed for 20 kilowatt, we should be able to operate 50 kilowatt for about few minutes, maybe, depending on the application. Then it should have a good peak torque. The size and weight have to be low, and it has to withstand high temperature. It should be able to operate at a high speed, because many applications required motors to be operated at very high speeds. For example, even in aerospace applications, other applications. So another advantage is power is equal to torque times speed, right? So for a given power, if the speed is higher, you increase the speed, the torque decreases to achieve the same power. So the sizing of the motor depends on the torque, okay, not on the power. It depends on the torque. The torque is proportional to d squared L. D is the diameter of the rotor, and L is the length of the rotor or the stack. So if you operate the motor at a high speed, the size of the motor can be reduced because the torque is lower. And it has to have a good or a high torque to inertia ratio, high speed operation, power density should have, volume of the motor should be low, high efficiency, low noise, and also it should have little or no maintenance, and it should be able to control. It should have good saturation characteristics. In a way, the saturation characteristics should be like this: torque versus speed. If you look at it, it should give you a flat, because many motors will have a torque which have a lower speed because it can get saturated. Okay, so we need to have a good torque speed characteristics and easy to manufacture, and also a lower cost. And also we should be able to have a good packaging. That one, packaging, space, and cost trade-offs are important. So the selection of a machine as part of an integrated system depends on the system performance and system cost. So if you have want to operate at the highest possible efficiency, then permanent magnet machines are better. But if you want to have a robust machine and less or more fault tolerant, less maintenance requirement, and that type of things, if you need, then the induction motor is better. So look at the characteristic of the induction motor. This is the torque versus speed for a given frequency. It is like this. So if you vary the frequency at different frequencies, the characteristic changes like this. This is up to base speed. Afterwards, if the speed increases, the torque decreases. So then you will have this type of characteristics. So the speed is controlled by controlling the frequency of the applied voltage. So generally, we operate the induction motor in this region. After this is called the pull-out torque on the right side of the pull-out torque. So we used to, in the earlier days, power electronics, before power electronics, it was direct online starting of the motor. Means directly voltage was applied, 480 volts, 3-phase, 60 hertz. Then the starting current was very high because there is no back EMF at 0 speed. So the back EMF has to build up. So they were using different techniques like star delta connection or putting a resistor on the rotor side and all those things. For a wound field induction motor, the rotor connection, rotor side resistance helped to reduce the starting current. But with power electronics, we can gradually increase the frequency, and so correspondingly the voltage is also gradually increased. So we can limit the starting current drawn from the source. So for example, in pump applications we use, so we can operate at different speeds, the pump 50% speed, 75%, 100%, and we can optimize the operation of the pump to achieve the maximum efficiency. The pump is selected, so the pump curve, this curve, intersection of the system curve gives the desired operating point. Okay, so at a certain point, this is the one. So this is the desired operating point, and at a 75% speed, this is the desired operating point, and at 100% speed, this one is the desired operating point. So we can vary the speed of the pump that allows the flow to be controlled. Where do we use the pumps to pump certain fluid? Okay, so the flow can be controlled by shifting the operating point without energy losses, with restricting flow external to the pump. So the amount of flow can be controlled, and the operating point can be controlled, and the speed can be controlled. Then we look at the power converters. As I mentioned earlier, we can have a rectifiers and choppers for DC motors. There is controlled rectifier. Okay, why do you need what is a controlled rectifier? Controlled rectifier is if you have a particular fixed voltage, fixed frequency, say 480 volts, 60 hertz. This symbol is the thyristor symbol. So we can have a variable voltage at the output, variable DC voltage at the output. Okay, there is a controlled rectifier. So instead of thyristor, if you use a diode rectifier or diode bridge rectifier, it is a fixed voltage. You cannot vary the voltage. Is a DC. Okay. So the diode bridge rectifier will not be able to control the output voltage, whereas the thyristor controlled rectifier is able to vary the output voltage. So you please go through all the items that you learned on thyristor converters, so that will be useful. So you have a 3-phase supply, then a controlled rectifier, then you get the controlled voltage. Okay. So thyristor controlled is controlled using this logic switching board or logic switching system. It can be implemented using DSPs or logics or any other or discrete circuits, doesn't matter. Or we can use the inverters for AC motors. So if it is an AC motor, so we use an inverter using say IGBTs or MOSFETs or anything depending on the power. So DC is converted to AC of variable frequency and variable voltage. So how do you convert DC to variable frequency, variable voltage? We can use sinusoidal pulse width modulation, or space vector pulse width modulation. So if you have taken EC 6305, you must have already studied this one, so please go through them again. The space vector modulation or space vector pulse width modulation is most commonly used in the drive systems these days. Okay. So we can control the output voltage and frequency. Cycloconverters, we convert three-phase AC to three-phase variable voltage, variable frequency AC at the output. So this is an example of a power converter for AC motor drive. So we have a AC power line, constant frequency. Then this is a controlled rectifier. This is a DC bus and an inverter. This doesn't have to be a controlled converter. This can be also a diode bridge, okay? Because the voltage and the frequency, the output is controlled by the inverter. So this can be fixed. Suppose if it is a square wave inverter, then this has to be variable voltage, because in square wave inverter, you can only control the output frequency, but not the output voltage. Okay. So then it goes to the motor. Yeah, this is the diode bridge. This is the converter, three-phase AC. And this is the DC bus. And this is the inverter and the motor. So we can also use a thyristor converter, but in that case, we can vary the output voltage, but it is not required if you don't want to put the power back into the AC source. So generally we use active rectifiers these days. That is the rectifier using active devices, like this type of bridge is repeated here using IGBTs, for example, or a MOSFET, depending on the power rating, so that we can control the output voltage, and also we can control the input power factor. So go through the active rectifiers also. But the only thing with the active rectifier is you cannot control the output voltage to zero. The minimum output voltage at the output of the active rectifier is √3 times line to line voltage. So that is the, or I mean, line to line, sorry, √2 times. That is maximum line to line voltage. So 480 is the, say, line to line voltage, then it is √2 times 480 volts. Or √3 times the phase voltage times √2. √3 times V phase times √2. So this is the RMS. So RMS, okay. So √2 times line to line voltage. So what type of power semiconductors are used? We can use a diode for a simple diode bridge rectifier. We can use silicon controlled rectifier or a thyristor, they are same. Insulated gate bipolar transistors, that is IGBTs, or a insulated gate controlled thyristor, IGCTs. These days, there is a lot of emphasis on the silicon carbide and gallium nitride devices. So these devices can operate at high frequency and high temperature. So you can switch at very high frequencies. For example, gallium nitride, you can switch even at a gigahertz. Yeah. Or yeah, megahertz, I would say. Several megahertz. Yeah, several megahertz. Silicon carbide devices can also be switched at high frequencies in the order of several hundreds of kilohertz. Okay. But silicon carbide devices are available at higher voltages. Gallium nitride devices are not available. Maximum available is 600 volts. So if you want to operate at high frequencies of the order of, say, 500 kilohertz to 1 megahertz, then gallium nitride is the best. Okay. So these are some of the characteristics. If you have a high current and high voltage, which device you use? For example, if you are in this region, this is 2000 amperes, the voltage is high, you use the silicon controlled rectifiers. If it is a little bit lower voltage, but you can go to higher currents, then GTOs, that is gate turn-off devices, or IGCTs can be used. Then if the current is of the order of hundreds of amperes, then IGBTs can be used. The controllers implement the control strategy governing the load and motor characteristics. So why do we need a controller? Controller is required to make sure that the actual value corresponds to the reference value. For example, if we want the motor to run at 1000 RPM, when there is a change in the load, for example, load is increased, then the motor speed might go down to 950 RPM. But we want the actual speed to be 1000 RPM. So what the controller does is, it takes the error between the reference value and the actual value, and then process the error in the controller and suitably adjust the pulse width modulated signals that are given to the power converter devices to achieve the required voltage and frequency at the output of the power converter output. For example, in this case, an inverter output, to control the speed of the motor in such a way to achieve 1000 RPM for the new load. So to match the load and motor, the input of the power converter is controlled by the controller. So this is the high-level block diagram of the controller. We have the torque and speed position commands, and we measure the actual torque, speed, and position and given to the same controller. In addition, we also measure the pressure, temperature, etc. from the load side as required. And then the current and voltage of the motor, and also the power converter status signal, like whether it is working properly or not, depending on the temperature, etc. So the controller processes all those signals and derives the required voltage and frequency to be given to the motor to achieve the desired torque, speed, or position. So these are the input signals to the controller, like torque, speed, and position commands, and the torque, speed, position, actual values, then the temperature and other feedback signals. Finally, we get the voltage, the frequency, or the current that needs to be supplied to the motor. So the input to the controller consists of torque, flux, speed, or position commands, and also the rate of variations of the signal to facilitate soft start. Means we don't want to apply the full voltage to the motor, then the starting current will be very high. So we want to have the soft start. We want to ramp up the speed. Okay. And the actual value of torque, flux, and speed, and position for feedback control, these are other set of inputs. And also the limiting values of current, torque, acceleration, etc. For example, the motor is designed for 100 ampere. We want the current to be limited to a maximum of 150 amperes. Then this value is also to be given to the controller. Then we want to keep the controller or adjust the controller to make sure that the power converter and the motors are at the desired temperatures. For example, we want the motor to operate within its temperature limits. Same thing with the power converter. So we measure the temperature and the controller checks the temperature of the motor and the power converter and accordingly adjust the load. So this is a block diagram of a servo control system where we are interested in the position control. So if you look at the load, and this is the motor is driving the load. So we may use the gearbox depending on the speed required for the load and also the operating speed of the motor. And the power converter feeds the motor with variable voltage and variable frequency. Okay, so we have the position information, then we have the speed information from a tacho generator. This is the position information from the load, position sensor signal. Then we have the current loop. Current loop is faster when compared to the velocity loop, and velocity loop is faster when compared to the position loop. The slowest signal loop has to be the outer loop, and then the inner loop, then the further inner loop, depending on the speed. For example, current is faster. That's why it is the innermost loop. Okay. So servo controllers offer extremely fast response and precise control of acceleration, deceleration, speed, and torque. So they are designed with position loop, velocity loop, and current loop. So for the control of electric machines, we have the motor. We need to have, of course, we are going to control the motor. So we need to have the motor, then the power converter, the load, encoder, tachometer, current and voltage sensors, and controller for controlling the power converter and overall control of the drive system. Okay, and this is the overall block diagram of AC motor control system. So which we have seen earlier also. This is drawn in little more detail. You have a three-phase power supply, rectifier, and a filter, inverter, three-phase induction motor, then feedback the current and voltage, then it goes to the controller. Then we have a gate drive signals. Basically, it has to be isolated. That's why it is the isolator. And this is the feedback on this one. These are the signals that is going to the gate drivers. So that is the main block diagram of the AC motor control system. So as we progress towards other topics, we will discuss more about these motor control systems, both for DC and AC motor drives. In the next class, we will talk more about the load and the load characteristics and how do we match the characteristics of the load with the motor. Okay, thank you.